Hello friends, we will talk about some pharmacodynamic concepts today, and I will be starting with what are agonists and antagonists. So giving a brief uh, overview of pharmacodynamics, it is what the drug does to the body. So means the effects which are provided by giving the drug. So starting with this drug, it will go inside the body. As we have understood pharmacokinetics, the drug will go inside the body, it will be absorbed, distributed, metabolized and excreted, and during all these processes it will also reach its site of action. And the site of action is the area which provides something what we call as a receptor. Okay. Now this receptor is a substance to which the drug goes and binds. Okay. And then after binding of that drug to this receptor, say for example this drug, it binds to this receptor and then you see the effect. Okay, so this is the chronology. The drug will bind to the receptor and receptor will, then this drug receptor concept, this complex, it will provide you the effect. Now coming to what are these receptors? Now receptors, the human body, it does various physiological functions, and those physiological functions, they are subserved by these receptors. The drugs only modify those physiological processes. So these receptors are normally present inside the body for substances like neurotransmitters or hormones or for autocoids. Okay, so receptors are already present for these drugs. Just what they do, they utilize the same receptors which are responsible for action of the already the what we call as endogenous substances which are released inside the body for doing some physiological functions. So this drug, it will not create any new process, it will just utilize the already ongoing processes inside the body. Okay, so now these neurotransmitter, hormone, autocoids, all these which have receptors, these can be combined, they can be called as one term called as ligand. Wherever you read this term, you know that these ligands are those substances which bind to a particular receptor, whichever is in question. Okay, so the drugs, what they will do, they will, just like the ligand, they will go and bind to a similar receptor depending upon their chemical structure. Okay, now now these drugs, they can do one thing. They can behave like what we call as agonist, and they can behave like antagonist. We'll come to this now. So agonist is a drug which behaves just like the ligand. Okay, means it will go bind to the receptor and it will show the same effect which the ligand is showing. Okay, so giving the drug and providing the ligand is one and the same thing. Okay, but the thing is, the drug may have a different mechanism, a different duration of action. So what we are doing, we are just amplifying, or you can say we are just sustaining the already ongoing process in this case, if the drug is an agonist. And we call it a full agonist if the quantity of the effect, or if you quantitate the action, uh, as much action or as much response is seen with the ligand, the same is seen with the full agonist. Okay, means if the ligand has an activity of 10, the full agonist will also show an activity of 10. Okay, so this is a full agonist. Then there is another term called as a partial agonist. A partial agonist is, you can, by the name you can guess that partial agonist is not like the full agonist. It will not show you as much as a response as will be shown with the ligand or with the full agonist. So a partial agonist, if the ligand is showing a response of 10, a partial agonist may only show a response of 5. Okay, so that makes the partial agonist important in a way. Why? Because if the ligand is present and you have also given the partial agonist, what will happen? They will have a competition between each other, and if the partial agonist wins, you will see a response only of 5. Okay, and if the ligand is absent, again you will see a response of 5, which would otherwise be 0. So the activity of the partial agonist depends on the absence or presence of the ligand. Okay, so if the ligand is present, a partial agonist will behave as an antagonist because it is suppressing the action of the normal ligand. But if the ligand is absent, the partial agonist will behave like an agonist because it is, at least it is increasing the activity even though the ligand is not there. So that makes the partial agonist an important drug, and especially in those cases where some level of activity is very much required. For example, some stimulation of the beta receptors is kept whenever you are using a partial agonist as a beta blocker. Okay. Okay, then coming to the third term, that is what we call as antagonist. Antagonist is a substance which blocks the action of the ligand. Okay, the agonist was mimicking the action of the ligand. Antagonist, it blocks the action of the ligand. Means whenever the agonist is present, the ligand will not be able to show its effect. Okay, so this is about the antagonist. Now, and then there is one more term, what we call as inverse agonist. Okay, inverse agonist is a substance which actually decreases the effect of the ligand. Okay, whenever this is given, the action of the ligand is actually reduced. The antagonist just blocks. It just does not allow the ligand to show its effect. But inverse agonist goes towards the negative direction. Whenever inverse agonist is present, your action will be towards the other side. Okay, so this is about the inverse agonist. Now when we are talking about all these substances, so what we see is there are two very important concepts in this. There is one thing what we call as affinity, and another is what we call as intrinsic activity. Okay, so there is one thing called as affinity, another called as intrinsic activity. So affinity is the ability to bind. It is, you can say, it is the love for the receptor. So ability to bind to the receptor, it is called as affinity. And intrinsic activity is ability to show a response. Okay, so ability to show a response is the intrinsic activity. Now as we are talking about agonist, so agonist will be having, obviously it has to have an affinity. Okay, all right, because affinity has to be there. That's only if the affinity is there, then only the agonist can bind to the receptor. So affinity has to be there, and also since I told you that agonist shows you a full response, so it will also have a maximum intrinsic activity. Okay, so intrinsic activity also will be maximum, just like the ligand. Okay, coming to the other thing, that is the antagonist. Antagonist will have affinity, obviously, because it is binding to the receptor. but its intrinsic activity is 0. Being 0, what it does is it only blocks the action of the endogenous ligand, does not do anything else. Okay, then coming to the third thing is partial agonist. And the partial agonist, what it does, it will have affinity. Again, affinity is there, yes, but the intrinsic activity is submaximal. Submaximal means it will lie between, if I give agonist a degree of 1, it will lie between 0 and 1. Okay, and then coming to the inverse agonist. In case of inverse agonist, what happens is, inverse agonist, here affinity is there, yes, affinity is full, but the intrinsic activity is towards the negative side, so it is 0 to -1. Okay, getting all this? I hope I am clear as of now. Now let's move a little bit further. To understand the concept of, you must be confused what is happening with the inverse agonist and partial agonist. I'm just going to give you a little bit more about that. Now see, the receptors which are present on the cell, they can be seen in two conformations. One, what we call as a receptor, normal receptor, and another is a receptor which is activated. Okay, and both of these, they are in a state of equilibrium with each other. Means normally whenever there is, even when there is no ligand present, some of the receptors may be in this state, or this what we call as an active state. So if it is an ion channel, for example, so if there are, say there are 1,000 receptors in total, maybe 100 are already open even without the ligand. So this activity, this is what we call as a constitutional activity. Means a receptor, even without the presence of the ligand, is somewhat in a active state. Not all, a few of them. Okay, so what these all these agonists and antagonists, what they do is, the agonist, it will bind to the activated state, okay, and it will stabilize this state. So the equilibrium will be shifted towards the active side, and more of the receptor will become activated. That's why agonist shows you a positive response. Okay, so agonist will bind here, and what it will do is it will increase the activity because it is opening more receptors. What about antagonist? Antagonist will bind to both these, the inactive as well as active, with equal propensity. So it will hold this state, and it will not allow any change in this state which was normally present there. Okay, so it will not allow the ligand to act, and it will hold, it will stabilize both these situations, and it will just stick to stopping the reaction or stopping this equilibrium at this point. Okay, then third is partial. Partial agonist will bind to this active state, but not as avidly as is seen with the normal agonist. Okay, and coming to the inverse agonist will bind more to the closed state. So what it will do is, it will bring this equilibrium towards this, and this constitutional activity will go down. When this goes down, obviously you will see an effect which is negative. Okay, so that's why we say that in inverse agonist, the intrinsic activity is on the negative side. It is 0 to -1. Got this? I hope this concept is clear. Okay, so now these agonist antagonists, they can bind either to the same site as that of the ligand, or they may bind to another site, what we call as an allosteric site. So they can say, if this is an this is a receptor and this is a receptor binding site. So agonist, you know, the ligand obviously it binds here only. The agonist may bind here, or it may bind somewhere over here, what we call as an allosteric site. Okay, this drug it can bind either on the same site as of the ligand or an allosteric site. If antagonist binds here, it would be called as a, if antagonist binds to the same site as that of the ligand, we call it as a competitive blockade or competitive antagonist. Okay, and if it binds to the allosteric site, it will become a non-competitive, obviously, because there is no competition for the binding site. The antagonist is blocking the action of this receptor by binding to another site, what we call as an allosteric site. So whenever there is no competition, there is one more thing what we call as since you know competition, in competition what happens, whoever say for example in a class when there is a competition, then the student who gets more marks will be the topper. Okay, so in this case also, if the ligand and the antagonist, whichever has got more power, more number of molecules, it will be the winner. Okay, so if the antagonist is more, the ligand will not be able to bind, and if the ligand is more, the antagonist will not be able to bind. So this antagonism, it is what we call as, it is surmountable. Whenever you add more of the ligand or the more of the agonist, the effect of the blocker will be gone. Okay, but in case of non-competitive, since they are not fighting for the binding site, uh, the effect will not be like that. The ligand, even if you add a lot of ligand, a lot of agonist, being non-competitive, it will not affect the activity, because it has the antagonist has bound to the allosteric site, and it is not binding to the ligand binding site, so there is no competition. So non-competitive block, what you see is the maximum effect of the drug is reduced irrespective of the dose. Okay, but in case of competitive block, what you can see, the maximum effect can still be produced if you increase the dose. And what is this maximum effect, that I will discuss in the next class, and that will be regarding efficacy and potency, and that will give you more clarity about this. Thank you so much.